about the HDFS in detail. Right, so we discuss what does a name node do. So name node stores the metadata of your file system. You have a secondary name node which is there, and it plays a very significant role in Hadoop 1. And the major role of this component is to have a backup of your name node. So in case your name node goes down due to some issues, then secondary name node comes as a savior of your cluster. And what it do, it just copies and merges your FS image and keeps a backup of it. So we can always take this file and recover the cluster back. Then we discuss about the data node. Data node are the slave components which perform the actual storage of your data blocks. And data node also have a task tracker component which runs on top of it. So task tracker will be executing the given task from the job tracker. Now what is job tracker? Job tracker is a master component. It will divide your job into a small task and it will give it to the small lot of task trackers to run them in parallel. Right, so that's about the HDFS. We also discussed about how do we write a file. So what are the different steps involved while writing a file into the HDFS, and what are the different steps while reading a file. So reading of a file, it goes through the name node. So first step is to go check with the name node where exactly is the blocks for a particular file is located, and then connect to the respective data nodes to read those blocks. Once all the blocks for a file are read, then we say that reading of a file is successfully completed. The same thing goes for writing a file as well. So while writing also you have to talk to the name node saying, okay, I want to write some file. Name node will check the permissions, and if you have everything, so it will make an entry of that file. And also the file is not existing, so you can never write a existing file. Right? So name node will check whatever file you are trying to write does not already exist. So in HDFS you cannot uh, write a file, or any file system. If the file is existing, you cannot write the file with the same name at the same path, right? It will give you some exception. So, and then it will, once it gets a list of the data node on which the blocks are to be stored, so it forms a pipeline of the data node and the write process starts. So the data file will be broken down into the small packets and it will be written on the data node. The data nodes will communicate with each other and they will replicate the blocks. So this process is not going to write 3 times, right? So data node will automatically replicate the blocks. The write process will only go once to one data node. And once all the packets are successfully written, then it says that, okay, the write operation is successful. We also talked about the replica placement. While deciding on which nodes the replica will be placed, the Hadoop tries to distribute it as far as possible so that we can recover the data in case of failure. So it never tries to write everything in the same node, it tries to put it on different nodes. And if you have different racks, it will try to put it on different rack as well. The first copy, if it is written on the same node, the second replica will be placed on a different rack, and the third one will be placed on a different node, not even on that node. And so that in case of failure, we have a copy save somewhere. Right, so these are the some of the concepts we discussed last class. Alright, so today we'll continue, but before continuing, I'm going to give you a link which you can start downloading. So if you type HTTP sandbox download, it will take you to the Hadoop sandbox, from the Hortonworks. Now in this website, there are, if you click on download sandbox, So there are different releases which we can download. So 2.5 is the latest one. Before that, there's a 2.4, 2. Just a second. If you click on Hortonworks Sandbox Archive, there are some previous version also like 2.4, 2.3, 2.2. So what happens is if you go with the 2.5, this will have the latest version of software, but it needs more RAM. So if your laptop or your VM has, not on your laptop, but your VM has 2. Not 2. More than 8 GB of the RAM, then only you can try all of these things. Right? Otherwise, you can go with 2.2 or 2.3, any one of this. So they also need near to 6 to 8 GB of the RAM, but it should be okay. It will slow down a little bit, but it should be fine. So now there are two links for them: download for the VirtualBox and download for the VMware. These two are the player, and these are the images. So if you click for download for the VirtualBox, then you need to install the VirtualBox first. And VirtualBox also comes free. So you can click it from here. And then once you have installed the VirtualBox, or you can start downloading this one as well. VirtualBox, the install guide is also there. So this is guide for the VirtualBox, this is for the VMware. Right, so I'm giving you this link. And you can start downloading now, so by end of the session we can install it.
Yes, do we need to install the VirtualBox and the HTTP, or we can directly install the HTTP directly on top system?
No, this VirtualBox you need to download in your laptop, which is a Windows host. Okay. Once you have downloaded this, you'll be able to play. These are the images. So these are this is a sandbox which has a Linux image of your Hortonworks software. Right. So what they have done, they have taken a Hortonworks software, they have installed it into a Linux a VM, and the image of that VM is what they have uploaded over here. So if you click on download for the VirtualBox, so it will ask you those details, and then once you accept, you'll be able to download it.
Okay. So the order is first we need to install the VirtualBox, and then
No, there is no order. So I mean, you can download both of them, but yeah, first install the VirtualBox, and then once you have the VirtualBox, you can double click on this, or you can import this image into the VirtualBox, and you can play it. Yeah, so let's download these two things. So let's say you can try. So Priyanka can try something older version. So let's say she can try 2.2.4 or 2.2. Right, so this will not need a lot of RAM, and you can try the latest one, HTTP 2.5 or 2.4, because these components would need more RAM. Okay.
how
So
much for 2.5?
it needs 8 to 9 GB in your virtual box, so in your VM, which should be sufficient if you have a 16 GB laptop. Alright, so while you are downloading, we'll talk about MapReduce.
So can you please share the virtual box, the link?
Yeah, I already shared it. First one. Okay. So we discussed about HDFS, and the next concept is MapReduce. Now, MapReduce is a programming model. So it's not a programming language, or it's not a specific tool which is used, right? So it's a model which is defined to process your data, right? So it is used for processing a larger set, use volume of the data, and that too in parallel. So if you have a lot of computers, lot of CPU around, and you want to run your any program in parallel, so MapReduce is a way to go with. So it gives you some of the way to decide how you want to break down your problem into smaller units, right? So this model says that your input data, first you have to divide it into key value pairs, right? So that process is known as a mapping process. So the map process will take some input key value pair and it will give you output as a key value pair. The second step is a reduce step. So it is kind of an aggregator, right? So it's going to collect all your keys and it's going to group all of them together to give you the output. Okay, so there are two steps: mapping step and you have a reducing step. Now, why we need to use MapReduce? The reason is, if we want to go for a large scale data processing, which means I want to run my data processing on thousands of the CPUs, but I don't want to manage the things. So if I need to manage the thing, there is lot of things that I need to consider, like which node to start the job and how to check which one is done or not, how to check which one is failed in between, and how is the optimization going. Right? So if I don't want to manage all of those stuff, but still I want to run my job on thousands of the CPU or the thousands of the nodes, then I need to go with the MapReduce. What it provides you automatic parallelization and the distribution. So a, a developer or a user will not be doing anything to parallelize or distribute your job across the nodes, right? So MapReduce will do that. Fault tolerance, it provides you an automatic fault tolerance. What it means is, if some of your task failed, so automatically it will restart and it will retry, right? So instead of a user running a program due to some, so if you have issue in the data or if you have issue with the code, so definitely no matter how many retries you do, it will fail, right? But if there is some network related issue or there some temporary breakage somewhere, so the retry might help, right? So those type of things it will try to do. IO scheduling, input output scheduling, MapReduce can do monitoring and the status updates also it provides. Right, so all of these features are readily available in the MapReduce, so we can use this and write our program in the MapReduce version so we can achieve the parallel processing. So all of those things, all of those features, and the one which is very important is it scales very well. What it means is, let's say you have 1 terabyte of data and you have 10 nodes. So if we are running 10 nodes to process 1 terabyte of data and it is taking, assume, 20 minutes, right? So if you want a much better performance, then you can even try out to make a 50 node or 20 node, right? So that will bring down your time because you will have more number of resources, more number of uh, mappers, and the reducer process can be started because you have more resources in the cluster. Right, so that many number of parallel process can be started, so that will bring down the time. Right, so what did we do? We did not made any changes in the program. Right, all we did is expanded the cluster, and the same program runs without any modification, and it gives a faster result. Right, so that's the advantage of using MapReduce. So this is how it works. So assume you have a data store, which means you have a file. So the moment we store a file into HDFS, we know it is getting splitted up into the HDFS blocks. Okay. So any file we store is going to be broken down into the smaller blocks of the data. Then each of these blocks will go through a mapping process. So all of this file, whatever you have in this data, will go, each of the line will go through a map process. Then this block will also go through a map process, this one also, this one also. So all the blocks will go through mapping process in parallel. The output of the mapper will be key value pairs. So assume this map has given you K1, K2 and K3, these three different types of the keys. Okay. The same for here also. So you over here also you have K1, K2, K3. So all of these mappers, it has given in the output the key value pair, which is three different types of the keys, right? Then once you have this intermediate data available, the next step is how you want to aggregate and reduce them, right? So there is a barrier, which is aggregation layer, which performs the grouping and partitioning of the data based upon the key. So this barrier is going to perform the group by function, right, or the partitioning function, and it's going to decide which key will go to which reducer. So if I have three reduce process running, so each of the key will go to one reducer. So K1 will go over here, K2 will go over here, and K3 go over here. So all the data for K1 will be grouped all together by this reduce function. The final will be the K1 and the final output that I want. K2, all the data for K2 will be going on this reducer. It will produce the final output for the K2 key, and same it will do for the K3 key, right? Uh, why we do all of these things? Because I can process my data in parallel. So mapping process running in parallel, reduce process running in parallel, and finally resulting in savior of the time. Right. So what we have, map task. Then we have a partitioning function. So this question is asked, like, when does the partitioning of the data happens, and where on which node it happens, right? So this diagram shows that you have a map task 2, map task 3. So each of the map tasks will be generating key value pair, and then it goes through a partitioning function which partitions the data based upon the key and stores it on the same node, the node on which the mapper has run, right? And then the reduce task will collect those data from different nodes and then run the reduce process over here. Okay. So this process in between is known as short-term shuffle phase. Your data will be shuffled from one node to the another node because it has to go through a reduce process. So if you carefully watch, in this node we had K1, K2, so all the data for K1 and K2 we had. In this node, in the output of this map task, we had K3, K4 and K5, where we had K4, K1 and K3. So which means this is how your data is processed and the outputs are available. So after the partitioning, all the data for, so if let's say this reduce is taking up 3 keys, so K2, K4 and K5 is coming over here, and this one is taking K1 and K3. So all the data for K2, so K2 from here will come over here, right? There is no other K2, so you see only one V, right? So only this one came over here, and this is sorted and the group data that we are receiving over here. K4, right? So this sorting and the grouping, so it's going to collect all the data. So K4 data will be coming from here and here and here, right? So you have 3 V's over here, 1, 2, 3, right? So once the data is collected from the output of the mapper, it's going to sort them and group them by the key, and the final result is this grouped data goes to the reduce function to give me the final output of the reducer, right? So you have a reducer running to give you the final aggregated resultant output, right? So even though we call MapReduce as a two-step process, but internally if you see, you have mapping process, and then you have a partitioning process, you have a short and shuffle process, and then you have a reduce process, right? So in between this, there's a data flow which happens across the nodes, which is very, very crucial to understand, because a lot of optimization technique depends on how we can minimize the flow of the data which happens during the network, right? So say if you have a file and you have to send it from one node to the another, so there is a network latency. So it will take some time to transfer a file from one node to another file to another node, right? So if you have a lot of data moving from one node to the another node, so it needs a lot of time, and that will overall hit the overall time of the execution of your job, right? So while discussing the optimization technique, we will try to minimize the volume of the data which needs to be flowing from one node to the another node. Any questions on it? Are we good?
So, question: how many partitions uh, after the map? How do we decide how many partitions going to do? We need.
So say the partitioning function will be running on each of the node where the mapper is running. So this partitioning function, what it will do, it will just partition your data based upon the key. Okay. This mapper output gave you K1 and K2. Okay. This mapper output gave you the data for K1 and K2. This partitioning function will divide this K1 and K2 separately. Right. So that's the partitioning function will do.
And how does the map know that which one is the key of the file?
Right. So a developer has to tell, saying for this job, this is my key.
Okay. So if I have, say for example, in a file, if you take some simple EW file, so dimensions are facts. In each dimension, the key, target key, where you have more than 1 million keys. So how many is going to divide those 1 million keys into 1 million partitions?
Okay. Yes, you are right. It will do.
Okay.
Yeah, it will do that. And then all those partitions will be sent across the reducing side, right? So because you have so many keys, so you will have so many partitions. That is true.
Okay.
All right. So this is how it looks from the node level view. So it's not necessary that your one node will have uh, one mapper and that node cannot run a reducer, because many times people ask me like, okay, you have a mapper node and then you have a reducer node. So they make a picture saying a mapper node can only run the mapping task and a reducer node can run only a reduced task. So that is not correct, right? So this node level flow tells you the same thing, that it's not necessary that a node will be dedicated to a particular task. So any node can take up any task. So job tracker will decide, okay, which task has to be run on which node. So if a node get a task to run a mapping process, it will run a mapping process. Like in this case, node 1, first it got the request to run the mapping process, so it ran the mapping process. So node 1, node 2, node 3, they first run the mapping process. And then the sorting and shuffling happened, the data moved from one place to another. And the same node 1, node 2, node 3, they again run the reducing process to give the final output. Right? So mapping and the reducing are the tasks which any of the node can do. Okay. But the sequence is like, first you have to run a mapping process. Once you have a data output of the mappers available, then only you have to run the reduce process. And who will do that? So the MapReduce framework automatically do all of this stuff. Okay. Now MapReduce framework, the sequence of the operation looks like this, and this slide is very important to understand what happens internally if you submit a MapReduce job. Okay, the first step that you see over here is you write a MapReduce program and then you put it on the cluster and then you invoke a MapReduce program, right? So the first step which a MapReduce program will do is to talk to the job client, and the client will talk to the master to get a job ID. So each job, each MapReduce program will get a job ID. Okay, this is the first step. And this job ID will be a unique number to identify a job. Then the third step is copy the job resources. So this program, along with if additional information required, will be copied on the STFS. Okay, so it's going to create a directory with the job ID in the STFS, because STFS is a shared file system. All the nodes can access STFS, right? It's a shared file system. So all the necessary steps, all the necessary information like the program or any config file, whatever, it will be stored on this STFS. So user is not doing it. All is done by the job client, which is a internal API of the MapReduce. So user is just submitting the job. All this process is happening internally, right? Now, once you have copied all the resources, then the client will say, okay, submit the job. So job tracker will say, okay, now I got the request to submit, which means I need to start processing this or start executing this job, right? So the fifth step is initialize the job. So all the necessary things required to initialize will be done by the master, right? And the sixth step is retrieve the input splits. So what is input splits is one of the top interview question which is asked. So retrieve the input splits. What does it mean? Your file is broken down into the blocks, which are the physical blocks of, let's say, 128 MB. Okay, but mapper program will not read the data as a physical blocks. Okay, your mapper program will read it as a one input split. So there is a marginal difference between one block of the data and one input split. What is that? We'll discuss in next few minutes. But the flow is, once it gets the input split, then it's going to tell the task trigger saying, can you start, can you run a task? Right? So let's say that is a mapping task. Right? So the first will be the mapping task. So if this task tracker is there, the job tracker will say, okay, you start your mapping process, it will just say. Then this task tracker's responsibility is to retrieve all the job resources. So it's going to connect to a shared file system, copy whatever it wants to do, which is mostly the program and all other, if at all anything else is there. So it's going to copy all of them on this node, and then it's going to launch a child JVM. So JVM is a Java virtual machine. So in a child process, it's going to run that mapping task or a reduce task. Okay. Why it is creating a child JVM? Any guess why it is creating a child JVM and then running a mapping task or a reduce task? Because task tracker is also a Java program. Okay, and a Java program runs in a JVM itself. Right? So why it is again creating another JVM and then running this process? Can you guess the reason why? Okay. So the reason is, if this program crashes or it has some problem which can create cost, which can blow up the entire JVM, assume, so this task tracker will be down if it don't put it in a child JVM, right? So it don't want to do that. Instead, it just want to create a child JVM and then run the task, because this is the actual program execution, right? So even if this JVM goes off, so it can create another JVM, right? So that for each of the tasks, it will have a separate child JVMs created. So each task do not interfere with the another task, right? So that's the purpose for starting everything at child JVM. This is the flow of our MapReduce program. All right, so we're talking about input split. Let's talk about input split. So yesterday we discussed, like, you have any file will get broken. At the moment we store it into the STFL, it will be broken down into blocks of 128 MB, assume. But there is a reason why I cannot take this 128 MB and give it to a mapper. And this is the reason why. So assume you have a file which looks like this. Kind of this. Let's say this is your something like this. Okay, so if this is my file, assume you have a text something like this. Okay, and this is a text file. You have so many lines, a lot of lines. Now, if I need to store this as a physical blocks of the data, it might happen like if assume the first line and up to, let's say this first line and this, okay, this much of the data is 128 MB, assume. So because it's quite possible, like your some of the word might get broken and this will constitute your 128 MB. So this could be your block 1. Okay. And then your block 2 will be in the sequence. So it's going to, let's say, read it like this. And then this is your block 2. This much of the data is 128 MB. So block 1, 128 MB. Okay, this is block 2, which is again 128 MB. Okay, and then you have block 3, which is again 128 MB, or whatever is the leftover, right? So let's say this is only 100 MB, like this. Okay, so this is how your physically the files will be splitted and stored on the STFS. Now, if you see carefully, we have broken down the words because physically they were not fitting into the block size, so they got splitted up, and because it is stored in a block format, in a binary chunk of the data, so it's quite possible that we have splitted the words in between, right? So if you blindly take this block 1 and give it to the mapper function, so this is how it will process. So let's say map process 1 is reading block 1. Okay. So, and assume take the same example that we did, the word count problem. Right. So it's going to map each of the word as the value of 1. So this is the key and value will become 1. Same thing is going to do with is, value is 1, a 1, file 1, 2 1. Okay. And then the last one T1. Right, so this is what a map1 will do. Similarly, map2, which is processing log2, what it's going to do, it's going to take the data of the block2. So st is the key for it, 1, the 1, right? So if you see, it is considering this one as the key and this one as the key. So while getting the count, you can never get the count for test. Right, same for the file also. It will consider phi as a word and le as a different word because it is running. It will be run by a separate map process. So you will never be able to get the correct count for number of the files that we have. Right. So actual it is one word, but it got splitted into 2 blocks. If I pass the block as is to the mapper, we can never get the correct output. Okay. So to avoid all of these problems, there is a concept of input split. So what input split will do, it will never split a file. Okay. So even though your physical blocks are like this, but your input split, while creating an input split, it will look out for the line terminator. Okay. So unless your record has a line terminator, it will not terminate it. So your first input split, let's say this is your so either it will break it over here till here only, right? It will not read the another one. So your first input split will be, this will be input split 1. The second line, assume this one, because it's not, it will continue till it don't find the line break. So this will be your input split 2, and this one will be your input split 3, because it will split based upon the line break, which is a new line character. Unless it finds, it will not break the record halfway. So if you have the input split going into the mapper process, there is no confusion at all, right? So each of the word are intact. You are not breaking a word in between. Okay. So instead of passing on the physical blocks, there is a logical block of the data which is the input split which goes to the mapping process. Is it clear?
Yes, and where do we save these input splits?
Input split is it's not a physical concept. Okay, it's a logical movement of it's a logical concept which is a logical split. So it's going to read this entire block. Okay, let's say if it do not find a new line character, it will continue to this, and over here it finds a new line, right? So it will give a mapper this much of the data, kind of this, right? So it's a logical split of the data. This will be generated only once your mapping process starts. See over here, only once. Initialize the job and then retrieve the input splits, right? So only once you have to process the data, it will be created. So it's not going to be created and stored on HDFS on some different location. That's not true. Okay. It will be generated on a runtime once the job execution starts. The actual location will be still the physical blocks of the data.
Okay, if that is the case, right? So you're saying the input splits are generated from the blocks.
Right.
So what? Okay, based on the size, whether the if that is the case, what if, say for example, if I have one unstructured data, unstructured file,
Hmm.
the chart we do in Messenger or wherever we do.
Hmm.
So if we do use a lot of shortcuts in charts,
Hmm.
say UR, U space or something like that we use, right?
Hmm.
How does the job or the whatever the logic splitting the input splits, generating the input splits, how does it know that is it a one word or uh, is it going to merge two words, UR, or how does it know?
Okay. See, it is not looking out for a word. Okay, it is looking out for a new line character. New line character is a enter. So in the chat box also you press enter to enter a new line, right?
Yes.
See, if I'm doing some chat messages, right? Hi, how are, and then I press you,
Mhm.
right?
Yes.
How are you doing? Something
Mhm.
like this, right? So if this is my chat, so that's fine. It's not going to consider like this is half word or full word, right? As long as you have pressed enter, so
Uh,
this is your one line. This is your second line. This is your third line,
gotcha.
right? So this one is a separate word. This one is a separate word. This one is a separate word. So if you pass this chat messages in a word count problem, it will tell you the count of R word is 2. 1 plus 1. U is 1 plus 1.
Okay.
How is 1 plus 2 plus 3? 3. Right? So it don't look out for a full word, rather it looks out for a line terminator in the data. Right. So this slide shows how does a short and shuffle happens. Okay. Sort and shuffle phase is again very crucial because you have your data which needs to be moved from one node to the another node. So take this example. You have one input split. It went to a mapping process. Now in the mapping process, first while generating the key value pair, right? So any program will be storing into the buffer memory, right? So it don't directly starts putting it on the disk, rather it creates the key value pair in memory, right? And then there is a partitioning process. So this partitioning is going to partition the data in memory, right? It's going to partition and then sort the data by the key. Now only once the volume of the data increases the threshold which is set for a buffer memory, the output will be spilled on the disk, which is partitioned by the key, and each of the partition, because it partition represents values for a set of keys or a particular key, right? Each partition is for a particular key, right? So that partition data goes to the copy phase, right? So copy phase is like you are copying a data. So let's say map task is running on node number 1, reduce task is running on node number 2, right? So somebody needs to get this data from here to here, right? So similarly, if this is K1, so this K1 data went from here to here, then on the another nodes also, wherever the other mappers are running, the K1 data will be copied from all of theirs, right? So all the K1 data has to be copied from the respective nodes onto the node where the reduce process has to run for K1. Okay. So all of this data came over here, and then there is a merging process. So K1 from here and then K1 from here, all the data will be merged together, right? And so all of these merged data finally go to a reduce process, and then you get the final output, right? So in between, if you see, this process is known as sort and shuffle. So you are shuffling the data from one node to the another node in order to reduce it. So we have a question: how many maps are there in a particular job? What do you think? Which one is the right option?
One level.
Priyanka, what do you think? How many maps are there in a particular job? Well, the answer is not configurable. The answer it depends on the number of the input split, right? Because yesterday we discussed number of the mapper is not configurable. It depends upon the number of blocks that we have, right? So if I have 10 blocks, then yesterday we discussed we'll have 10 mapper. If I have 1000 block, so the number of mapper will be 1000, right? So it depends upon the volume of the data, and volume of the data will determine number of the blocks. So actually, instead of number of the blocks, as we discussed today, like it depends upon the number of the input split. Is it clear?
Yes.
Right, so that's what we discussed, like number of the mapper will not be configured. It will automatically be generated based upon the number of blocks we have, and the number of the blocks will be somehow nearly equal to the number of the input split. So since each input split goes to one mapper, so number of mapper will be equal to number of input split. This is the right answer. D depends on the number of input split. And this question is guaranteed in any of the anywhere you go, people will, if any sort of interviews or certification, they will be asking this question: who determines the number of mappers? Okay, so the right answer is input split. Don't even say data blocks, right? So number of the blocks don't determine the number of the mappers. Yesterday we discussed that, right? But the correct answer will be number of the input splits, which determines the number of mappers. Okay. Can a job has a zero reducers? So can we have a job which is only mapping job? There is no reducer job. What do you think? Is it possible or not?
What if, I mean, my guess it is possible, because what if I don't have any, what if I have only one split? I mean, if I have only one block of size, why do I need to reduce it?
No, you definitely have to reduce it. Why not?
What if, what if I don't have any, reducing it to, uh, what is the purpose of the reducer?
What is the job of reducer? So
Yeah.
in this case, you had block one, right? So you gave key value pair like this. Okay. Now a reducer process is, unless you don't have a reducer process, you can never find what is the count of each word. Right, so you need a reducer to aggregate your stuff and tell you this is the count for each of the word. Right, let's say in this case, can you tell me, if you only have a mapper job, can you tell me what is the count of word, let's say what is the count of word, so, okay, if this mapper will be taking up, instead of block 1, if it takes input split 1, which is the actual case, so this is a, you will have a test 1, right, and file 1. This is test file 2. So you have file and 2, right? So this much of data will go to the mapper 1. This is the output of the mapper 1. Okay. Similarly, for the mapper 2, you will have test the execution of MapReduce. So test the execution of MapReduce like this, right? And then you have block 3, which is file is splitted. Kind of this, okay? Now, tell me, if I need to get the count of each of the word, can I get it by this output?
Yes, in this particular case, we need the reducer. What if I have only one very small file, it is less than 128 MB or one input split.
Okay, got it. So if you have only one input split, let's say, let's take this file, okay? Let's take the same file. Let's say this one is one input split, okay? Now my line is like this, my data is like this. Something like this, okay? This much of the data is going to my input split 1. Can I get the count of each of the word properly without a reducer?
So if you need the count, yes, you need the input split. Make sure that is one scenario. The other scenario I'm talking about, what if I know there is no duplication? I have in that file I have whatever the data I have, each and everything entries in the data is unique. So even though if you do the reduce, what if you already know that the answer is each and every count is one only?
Yeah, you don't need to run the program then, right? So if you, let's say if you need that each of the word is only one, and you don't need to run the program to get the count even, right? So that is true. So if you don't want to aggregate the stuff, like in this case we had,
In
uh,
the data, yes, I will just run the file,
hmm,
map, and full output. If I want to
right,
aggregate something,
right.
then we need to run the both map and the reduce.
Absolutely, that's the answer. Okay, if you have to aggregate the things, then you need a reducer. Okay, if you don't have to aggregate the thing, you don't need a reducer, only the mapping will do. So there are many scenarios where you don't have to aggregate the stuff. All you need to do is generate some output based upon the input. Okay, right? So instead of key value, let's say if I need, so if you have some records where you need you have some data, and then you need to just, let's say you have a file like this where you have a telephone number, let's say something like a telephone number, your mobile number, and then timestamp, right? So timestamp will be something like 2017 02, something like this, right? And then you have called party number, something called party number, and then you have duration in seconds 34, right? So if you, this is how your data looks like. And in the mapping process, I just want to know, like, this, what is the usage of each of them, each of the number, right? So I don't need to care for all other stuff. If I have 1,000 columns, I don't bother about it, right? So I will just say my key is the mobile number, and my key is this, and my value is the usage, right? So this I pass, and mapper will give me this result, right? So this type of cases you don't, because there is no aggregation you are doing, right? So you can only use a map only process, right? So the answer to this question, can a job has a zero reducers? The answer is yes, a job can have a zero reducers if there is no need to do any aggregation or any uh, final reduction of the data, which is like mostly it will be like any aggregation or all those things, and we don't need a reducer for that, right? Only map only job should be sufficient. Now there is one important concept which is known as speculative execution. Okay, so what happens? Speculative execution means somebody is speculating the way your jobs are executing. Okay, speculation means you are keeping a close eye, speculating like what's going on, right? So this process means whenever master job runs a task, right? So let's assume there is a job which master divided a job into 10 different tasks. Okay, now master will speculate how each of them are behaving and how they are processing the data. Okay, so it's going to take like how much of time normally a particular task takes for a particular job, right? So let's say uh, out of 10, 9 of them completed this task in 1 minute. Okay, but the 10th one is somehow slow and it is taking more than 1 minute. So assume it has taken more than the average. So average is assume 1 minute. So if the 10th one is slow due to some reason and it is taking more than 1 minute, say 2 minutes or 1.5 minutes or whatever, right? So if master comes to know that some of my task is running slower than the average, so what it will do, it will spawn up a duplicate task. Okay, and the duplicate task will be started on a different node, and all of this is done to ensure that due to some network latency or some issue with the hardware configuration of a node, it should not impact the processing or overall time it takes to process the data, right? Because if some of the hardware is down and you have some resources available somewhere else, so why not utilize the one which is working good, right? So that's the idea behind. So what it will do, it will start, the 10th task will be duplicated and it will be started somewhere else, and out of these two, the 10th task and the duplicate 10th task, whichever gives me the first, or which one completes first, the output of that will be taken and the one which is still running will be killed, right? So this process is known as a speculative execution. While executing your task, you are also speculating like how long it is taking, what is the average execution time, and then find out which one is not yet completed in that time and then do the duplicate and all of this stuff, right? So this process is known as speculative execution. So sometimes it could be an overhead also, which might impact your overall job execution time. So sometimes people turn it off, right? So it's all configurable. So if you feel like it's an overhead, so you can always turn it off. So turning off an executive execution will improve the performance of your jobs, right? So, but if you are 100% sure, like your networks, so all of nodes are of same configuration and all of your nodes are properly fine, there is no network issue and all of those stuff, it's advisable to turn this feature off so that your overall time will be better. Okay, any questions? Are we good? Any questions so far? Tinka, are we good? Okay, so did that download complete?
Not yet, 37%.
Tinka, for you? All right, so we'll continue. So let's also look into some of the more important concepts in MapReduce. All right, right. So this we have seen. Like if this is how MapReduce works. If you have an input word, first step is map everything with one, and then you aggregate them to get the count of each of them. And this is behind the scenes. So each of the input split. If you have many workers, okay. So in the mapping phase, the worker is going to read the input split and generate the key value pairs, right? So local write, which means like intermediate file will be written on the local disk. This is very important. This question is asked in the interviews. When many times people ask you, where does this intermediate output of the mapper is written, right? So the answer is it is written on a local disk. It is not written on the STFS file, right? So whenever a mapper process is running, it is reading an input split, but the intermediate key value pair will be written on the local disk, not on the STFS. Why it is done so? Can you guess why it is written on a local disk and not on the STFS? Because your input splits is in STFS. Okay, but why are we writing this key value pairs in not on the STFS? Why we are writing it on the local disk? So local disk means if this worker is running on node number 1, so it will write this intermediate output on node number 1. This one will write it on node number 2 and this one will write it on node number 3. And on the local disk of node numbers 1, 2 and 3. So there are two types of things. Each of the node will have a local disk and also the HDFS. Okay, SDFS is a distributed file system, but since each of them are a computer which has their own storage and its own memory and everything, so they have a local disk also. So can you guess the reason why it is storing on the local disk?
Maybe. Sorry, no guess.
See, if you store anything on HDFS, so first thing is it will be replicated 3 times, okay, because this is a default behavior of HDFS. Any file you store will be replicated 3 times, and these are intermediate data. Why you want to replicate it, right? It's not required at all. Anyhow, you have to delete it. Once this phase goes, you have to delete all these intermediate files, right? So this is the reason why this mapping process will be writing out on local disk and not on the HDFS. Okay, because we don't want to replicate this intermediate data. These are not crucial. This can be, if you rerun that again, you will get it, right? But these are the important data which is stored on the HDFS. This is your input raw data. So this is the reason why it writes all of this intermediate data on a local disk. Now once you have written all of this in a local disk, then there are, in the reduce phase, you have some workers which will be copying these files all across from this local disk, and then it will be performing the merging, right? So it's going to merge all of them together and then perform the reduce operation to give us the final output file. And this final output will be on HDFS, not on the local disk. Why? Because this is your final output, right? So you want to save it properly, right? So it goes on the HDFS. So your input is in HDFS, output is in HDFS, intermediate files will be on the local disk wherever the mappers are running. Okay, that's the flow. All right. I want to show you one of the MapReduce program, so it will be easier to understand. Okay. Now, are you aware of you are aware of the core Java, right? So this is very simple core Java implementation for a word count program. It's very simple. I will just show you what we are doing. So whatever we discussed in the slides, if we need to put it on a program, so this is how it looks. So we need to define a class which is a word count, right? In the main class, there is another class map, which is user defined mapper class. We call it as a mapper class. Okay. So it will be extending from the MapReduce base and it implements the interface of mappers. Okay. So it has input key, input value. So I'm saying that my input key is a long writable, input value is a text. So text is similar to the string. Long writable is similar to a long or long data type in Java. So all these data types are Hadoop specific data types. Okay, or a MapReduce specific data types. Long writable, text is similar to a string, int writable is similar to integer. Okay. Are you aware of Java serialization? Serialization and deserialization? Heard of those concepts? Are you familiar with them?
No, no.
Okay. Priyanka, what about you? All right. So that's crucial, right? So I would suggest as an assignment, you go and read about serialization and deserialization. Okay, this is a Java topic, which is, so I will just give you a brief background of this one. What happens is, if you have to transfer an object from one node to another node, so in Java, first step is to serialize them. So an object will be serialized, which means it will be written on a file in a way which, if you transfer it from one place to another place, so a deserializer can read this file and can find out, okay, what is the input of your object, right? So mostly for the data transfer from one node to another, or even to save the data and all, the serialization deserialization concepts are very important. Okay, so go take out some time and try to read about this concept. It's very important concept which determines the overall performance of your jobs. In a distributed environment, these concepts are very important. Okay, but once you get some idea, we'll discuss more on that. But this is what we are doing now. So you have some input key value pair, output key value pair, sorry, input key, input value, data type. So input is a long, value is a text, output is a text, and output key is text, and output value is integer writable. Now what we need to do, we need to map each of the word with one. That's what we are doing. So find static int writable is equal to int writable 1. So what we are doing, we are taking one object of integer as 1 and saying the value for this one is 1, numeric 1. Okay, and then we are taking one word as object of text. Now there is a function map. This map function is, we need to override this map function, and the programmer has to say what has to be done during mapping. So I told you, right, what is going to be the key and what is going to be the value, the programmer will decide. And this is how we need to decide, right? So in the map function, so first we need to do is take the input line as a line, and then, so we are converting this value into to a string. Is going to, so I'm reading it as a line, and then we are breaking this line into the words. So just relate it with this. Okay, these are the two lines. If I need to run the word count on top of this, so this entire line will be given to the map function, and then this line will be given to the map function. So input to the map function will be this line, each of the line of input split. So first line goes as an input. Okay, now what we are doing, we are breaking this line, we are reading this line and breaking this into based upon the space, we are breaking it into the words. So that's what we are doing over here. String tokenizer equal to new string tokenizer line. So once I say line, it's going to break this into the tokenizer. It's going to break it based upon the space. So by default, if space is a delimiter, so based upon the space, is going to break this line into the words. So it's going to give me the output something like this. It has broken down the line into the words, this particular line, right? So while tokenizer has more token, like while you have the tokens, like for each of the word, right? I'm setting the word as tokenizer.next token, and so word, the value of the word I'm setting as value of the next token, which means I'm setting the word. So in a while loop, right? While I have the words in the while loop, I'm setting the word equal to line, okay, and output dot collect, in the output I'm sending word and 1, which is nothing but I'm sending line and 1 in the output of my mapping process. Okay, and it will repeat for in a while loop. So for each of the line, it's going to do the same thing. So it's going to repeat it like this, is 1, example1 4 Okay, this will be output of my mapper programmatically. Okay. Now one thing important over here is the data type, because I wanted to send the word and the count, right? So word is my text and count is my integer. So same thing I defined over here. If you see, output collector I defined as key is my text and value is iterable. So whatever is the output of my mapper, the same thing goes as input to the reducer. So the next we need to decide, we need to define a reduce class. It will extend from the MapReduce base and it will implement the reducer interface. Okay. In this we have a function reduce. So what we are doing, we are taking an integer sum equal to 0. Now while value has next, so if you see the input of this reduce function is a text, I am taking it as a key. There is a iterable, there is a iterator of the integers, we are taking it as the value, and then there is the output collector which will collect the output of the reducer. Okay. Now over here what we need to do, we need to, for each of the key, so each of the key is, this is the key and all the values for a key is packed kind of an array into this iterator. Okay. So what I'm doing, while value has next, so while you have elements for a particular key, okay, you do the sum of the values, right? So sum equal to sum plus equal to, it means sum equal to sum plus value. So it's going to sum up all the values together, and in the output you are going to have the key and the sum. So it's simple, it's just for each of the key, right? It's going to key and it's going to get the list of the values, this is what goes to your reducers, right? So you get a key and the list of the values. So if your key is like this and the value is 1, right? So it's not going to do any 1. If your key is like this is, and the values are 1, 1, which means 2 values for this key. So it's going to sum it up together, right? And store the output like is and 2's. So that's what we are doing over here. While you have more values for a key, sum them together and then give the output as key and the sum. Then there is, in the main function, we need to write the driver program. So driver goes in a main. So driver, what it will do, we have to tell like what is my mapper, what is my reducer, where is the input, where should I put the output. All those stuff goes in a driver program. So you have a need to get object of the job conf. We are saying my job is word count dot class, because this is my main class, right? Word count. So I'm saying this is main class. Conf dot set the job name. I can also give the name of my job. Let's say this is the word count. Okay. Output key. What is my output key? Output key is going to be the text. Output value is going to be the integer. Right. So that's what we are setting over here. Set the mapper class. Mapper class is map.class because this is what we defined over here. Okay. Set the combiner class. We have not yet discussed about this. We'll discuss it now. And then I'm saying set the reducer class. So this is my reduce.class. Okay. And the next step is set the input format. So I'm saying the input data is going to be in a text format. Set the output format. I'm saying my output data is going to be in a text format. So input is text, output is text, everything is text. And then I'm setting the input path. So in file input format, set the input path. I need to specify the first argument is going to be the input path and the second argument is going to be my output path. Okay, so this ars0 and ars1 will be argument to this program specifying input and the output path. So that's all. Once we have configured all of these things, we just have to say job client on run the job, and this run job will finally invoke So this run job is something which is going to finally invoke the see this is the run job. Okay, so the moment you say run the job, you submit this run job is going to invoke the job client, and then job client is talk to the master. Master is going to give you a job ID, and then all of this process will flow, right? So that's how the flow is. You have to write everything in a program. You have to say what is going to be your mapping key, what is going to be your mapping value. Then you have to decide in the reducer what exactly you are going to reduce, right? And then submit it to the job, and then it flows. Any questions you want me to repeat, or is this clear? What do you think? Is this program clear?
Well, clear in terms, we understand what how we need to write it, but so far I never wrote any Java code. One thing, and
No, don't go on
it,
the syntax. I understand. So don't go on the syntax and all. I just wanted to show you the flow, right? So what
yes,
we need to see the flow is what is important is how how to write a program and what exactly things to be considered. This syntax and all is not difficult. You can use the same program to. You can always refer to another program to go to the syntax or go to the Google and all. What is important is the flow. What is coming as the input? What has to be done to get the output, right? So
yeah.
that's more important. Priyanka, is this clear for you? Right. So what we have over here is we have to decide. So everything is with the programmer. Now, in this case, we have not bothered. In this MapReduce program, we never bothered about thinking about how is my job getting executed, where it will be executed, how many mappers, right? Where exactly, what happens if something fails, what I need to do, how to retry a job, how much of memory I need to assign to. All of those things is all taken care by the MapReduce framework. We don't have to do anything. So as a developer, we just have to focus on the core logic, right? And that's the one of the biggest advantage of a MapReduce, that a developer is not bothered about how your job is going to scale out and who is going to distribute your jobs, on which nodes you are going to run it. You don't have to do anything. You just have to focus on the core logic, how you want to process your data. That's it. Once you have decided that, you dump it onto the framework, and the framework will take care of running your job. Right? In this program, we have never decided how to split a job, how I will get the data, nothing. I didn't bother about anything. Right? I just said once I get the data, as the value, what I'm going to do with the data. So first I'm going to break it down into the words, and then I'm going to assign each of the word with one. That's what I need to do in the mapper. That's it. 3 4 lines and I'm done with the mapper logic. The same for the reduce. What I need to do in the reduce, for each of the key I need to sum up the values. So that's what I'm doing. I'm just summing up the values and giving it on the output. That's it. Okay. Now this part, set combiner class. Right. So I just said we'll discuss now. So combiner is one of the way to optimize the performance. Let's see how. Okay, so now we understood, like, you have some input file which is broken down into the blocks of the data. These blocks of the data is going as an input split to the mapper process. Mapper process is going to divide it into the key value pair. This key value pair is going to be partitioned. The partition data needs to flow to the reduce process, and then reduce process is going to merge them together, and then it is going to aggregate and give me the final output, right? So this is the end-to-end flow. But how can I optimize those things? Okay, let's take one example. One of the way which a developer can do in order to optimize the overall time is use of a combiner class. And this combiner class is again very important concept. Okay, combiner, as the name says, you have to combine something, but combine what? Right? So you need to combine the data together. How? So let's see. In order to optimize the bandwidth, we have a combiner function. It acts as a mini reducer. Okay, so you have a reducer at the end which does the final reduction of your data, but during the map process also, if we can reduce the data, so that's going to optimize the overall performance, right? So that's what we mean by bandwidth optimization. Let's take one example. Say you have your inputs which uh, you have your input data which tells you for each of the year what is the temperature from different weather station, right? So if you see from some of the weather station, you have a in the year 1950, from some of the weather station you have temperature coming out as 0, from someone else it is 20, somewhere else it is 10, right? And then in the mapping 2 also, because your key is the year and the temperature is value. That's why we're just considering the key value pair now. Okay. So my input is a weather data set with the values which contains the year and the temperature. Right. So assume that is, so definitely it's, if you have a weather data set, it will contain many other things also. Like let's say weather station ID, at what time the temperature was recorded, what is the latitude, longitude, right? And a lot of stuff that a weather report will have, right? So if that weather report data you fetch, you give it to a MapReduce program, and I want to find out for a given year what is the maximum temperature. Okay, maximum temperature for a year across the globe, right? So if I need to find out the maximum temperature, so first step will be I need to divide the input into the key and the value. So key is my year because I want the maximum for each of the year, right? And the value is going to be the temperature. And finally, in the reduce process, I need to do a sum of them to give me the final output. Right? In this case, if you see this, so you have a key value, key value, key value, all of these things together. Now, if I run in a reduce function, if I run the max of all of these things, so for a given key, right? So this all belongs to the same key. Right? So the max will be the max of 0, 20, 10, 25, 15, which is 25, and that is the final output, right? So for this 1950, maximum temperature is 25. But how can I optimize the things? So there comes the combiner. If I have to optimize the things, I need to run a combiner. So instead of sending these 3 records, and output of this mapper as three records, and then output of this mapper as 2 records to a reduce function which is going to do this process. Okay, if I can combine the data within the mapper itself, right? So instead of sending 3 record, why don't you send me only 1 record with the max of, which is the max of each of the year, right? So that I don't have to do a reduction at the end, or the volume of the data which will flow from mapper to the reducer will also decrease, right? So instead of 3 line, if you send me 1 line, and this one is also instead of 2 line will send me 1 line, right? So what I need to do is I just have to do the max of each of the respective max, right? So why don't you guys do max in your own, right? So that's what it is saying. You do the max of these 3, right? And then you do the max of these 2, and then finally I will do, in the reduce process, I will do only the max of individual maxes, which will give me the final output, which is same as doing the max of all of these individual items, right? What is the advantage? Advantage is the volume of the data which needs to flow from mapper to the reducer, it got reduced. So instead of 5 line, now I'll be sending only 2 lines. Okay, if I have millions of the record, just imagine how much of the data we can avoid flowing from mapper to the reducer if we can use the combine function. Do you agree with me? No responses. Is it not clear? I can repeat it one more time.
Yes, please. Can you please repeat?
Okay, perfect. So see, let's go back to our example. Okay, you have mapping, and then you have a reduce, right? So and in this, let's say this mapping process is running on node number. Let's say there are 2 mappers. So you have mapper 1 and then you have map 2. This is running on node number, let's say this is running on node number 10, and this one is running on node number 12. Okay, and then you have a reduce process which is running on node number 5. All right. So in node number 10, you are getting the key values pair like this, 1950, and the temperature is 2. Then you have 1950 and temperature is 5. And then you have 1950, temperature is 0. And then you have 1960, or let's say 1951, temperature is 20, and 1951, temperature is 23. Okay. These are some of the key value pair which is output of my mapper 1. Similarly for mapper 2, I will have the same weather data set, so something 1950. In some of the weather station you have temperature as -9, right? And then 1950. Somewhere else you have temperature as 4, and then 1951 you have temperature as 3. 1951 you have temperature as 7. Okay, this is the key value pair. I just same to this, right? So over here, instead of passing the hard-coded value of 1, okay, for each of the year I'll be passing the temperature. Instead of the 1, I'll be passing the temperature, and that will give me the output of like this. For each of the year, what is the temperature? Key value, key value, key value. Now if this data has to be reduced, because definitely we need to reduce, right? I need the maximum for each of the year. So what a reducer will go, reducer is going to get the key, which is my 1950. This is my key, and the value is a list of all the values. So it's going to get 2, it's going to get 5, it's going to get 0, and then it's going to get -9, and then it's going to get 4, right? So this is one input. Okay, and the another input is going to be 1951. Okay, and the same set of values that we have, so 20, 23, and then you have 3, and then you have 7, right? So what a reduce function will do, for each of the key it will get a list. So if it gets this key, it needs to run the max function. So it will be running a max of all of these values. Okay, and final output will be 1950, and whatever is the max of it. So let's say if the max of this is 5, so it will give the 5. The same thing it will do for the another key also. It's going to run the max function on this data set. Okay, and then it's going to tell me for the 1951 you have the maximum temperature 23. This is what a normal flow would look like, right? Same as the word count. Instead of doing the count, now I'm getting the maximum. So instead of the sum, I'm using the max function and giving me the maximum temperature. Okay. So if you see, number of the lines which has flown from node number 10 to node number 5 is five records which has to be moved from node number 10 to node number 5 to get all of these 5, right? Same for node number 2. 4 records has to be moved from node number 12 to node number 5 so that this reduce function which is running on node number 5 can reduce all of this together. So total number of the lines that moved is 9, right? In this process, total number of the records moved, total records moved in network, so anything movement will happen through the network is equal to 9. Do you agree with me so far?
Yes.
Priyanka, have you good? Alright, perfect. Now, if I need to optimize this thing, okay, optimize in a sense because anything which goes through the network is costly because it will take a lot of time to move data across the network, right? So you are transferring the data from one node to the another. If your volume is larger, definitely it's going to take much larger time, right? So if I have to optimize this step, what does a combiner says why you need to send this 5 records? Why I need this 5 records? Why you guys cannot do the max and give me the max, right? So instead of this, if I can aggregate these 3 together for each of the key, and instead of sending this data, if I send only this 1950, right, and the max of this is 5, and then 1951, and the max of this one is 23, right? So instead of 5, I will be sending 2 records. Instead of 4, I will be sending only 2 records. 1950, max is 4, and 1951, the max is 7. Right, so what I have done, I have done the max within the mapping phase itself. In the mapper process only, like after the mapping process, I have done the max of it. So one more step to get the max of each of the individual mapped data. And then instead of sending this, what I will do, I will be sending only 1950. What are the values it's going to get? It's going to get from the first one is going to get only 5 and 23. Right? So, oh sorry, 1950 is going to get 5 from here and 4 from here. Right? So 5 and 4, these are the two values it will be getting. And for 1951, it's going to get 23 and 7. 23 and 7. Okay. So instead of a full set of the data, I got a reduced data, and my job to reduce is even much simplified. So I just have to get the max of 5 and 4, which will be 1950 and 5, right? Over here also it will be the max of 23 and 7, okay, and final output will be 1951 and then 7, okay. So total record moved through network is how many? Only 4, right? And see the output, the same output, oh sorry, it will be 23, okay. So the same output that we got in the first case, we are getting the same output in the second case also, but the time taken will be significantly reduced because we are, the volume of the data which is flowing from node number 10 to node number 5 and node number 12 to node number 5 is significantly reduced because I have reduced the data in the mapping phase itself. Is it clear now?
Yes.
Right, so this process is known as combiner. We are combining the mapper outputs.
So is it possible? So it's kind of combiner is also kind of reducing the output, right?
Absolutely, that's true. So that's the reason why we call combiner as a mini reducer.
Oh, okay. And see, our map 1 is on node 1, our map 2 is on node 3, but why is the reducer on the different node? What if, I mean, I don't know the possibilities, I'm just thinking, instead of moving data from multiple nodes into some other node, what if the reducer stays on one node where the data is, and what if you move the other node data to the same node? Is it possible?
How?
See, in the previous example, if you go to the notepad,
Hmm.
map 1 is on node 10, map 2 is on node 12.
Hmm.
So we are moving node 10, node 12 maps to node 5 where the reducer is exist or whatever the node is it is on. So we are moving two different sets of nodes data into some other different node that is 5.
Hmm.
What if reduce, is it possible to keep the reducer on the node 10 or 12 and move only one node data into the other node data?
Yes, why not? It is definitely possible. So if node 10 or 12 has some of the bandwidth, right? So it can run reducer. It doesn't matter. Even if it, let's say this reducer is running on node number 10. Okay. So this data volume is reduced. Okay. But anyhow, you need to move this node 12 data,
Yes.
right? If you have to move the node 12 data, this is only case of two reducer. If your file is 1 GB or let's say 1 terabyte, you will have thousands of the mapper running on different nodes. Right? So even though I run this node number on node number 10, which only map one job, that this much of the volume is good. But what about the 1,000 mappers which are running on 1,000 different nodes? They have to transfer or not?
Yes.
Right? So your problem is still the same, right? You can solve only negligible amount of time if you move, even if you move. But in this case, if you reduce the data, you are significantly reducing the volume of the data.
Correct. So do we, I mean, who decides where to run the reduce on which node? Do we decide?
No,
Framework
the
decide?
framework will decide where to run. So whenever any one of the node is free, it can run on them.
Okay.
Okay. So say running a reducer on a particular node will not solve your problem. Your problem is flow of the data. So you have to control the flow of the data, and that's why you have a combiner function to solve the problem.
Okay.
right? So this is known as a mini reducer. And that's the reason why even if you see the program, your mapper class is map.class, but your combiner class is same as reduce.class. Your reducer class is again reducer.class. So it's nothing but combiner. I'm saying you run this reduce logic as a combiner, so your data will be combined together in the mapping process itself.
Okay.
Priyanka, any questions? Alright, so now tell me one thing. If I need to get the average of temperature, can I use combiner? So instead of the max, if I need to get the average temperature for each of the year, instead of the max, I need to get the average temperature. Can I use the same combining logic that we do in the reduction? Is it possible or not?
I think we can, no, yes.
Yes or no?
Okay. That's what I'm calculating. I mean,
Okay.
if
Okay. Try
yeah,
it.
if I do the average first, and after, see, if I do first count the average on map 1, and then do average and map 2, move those two values into node 10 and do the average again, does it give the same result or not? That's what I'm calculating.
Yeah. Please try that. Priyanka, can you
Because
also try? Priyanka, can you also try? Is it possible or not? So let's take the same example set. Tell me, Priyanka, if is it possible to run the average on this data set? Is it giving the correct output?
one second, 2 plus 5, 7, 7 by 3 is 2 point something, and here minus 9 plus 2 by 2, 2.5, 2.5 plus 2 is 4.5 something. So if I combine all 7, 11, 11 minus 9, 2. I don't think you are not supposed to combine.
Why?
See, I mean, I'm just did the bare calculation. If we want to combine function is not only for to identify the max, right? To identify whatever the logic you're trying to achieve or aggregation you're trying to do. Say what we did was in the map 1 function, we have three different 1950 values. What is the average of these three 1950s? 1950 comma average of 7. I believe it's around 2 point something, right?
Yeah.
And map to average of 1950 is minus 5. Minus 5 by 2 minus 2.5. 2.5 to 5 almost 0. 0 temperature. The average is 0.
Okay.
Maybe I'm doing wrong calculation, I don't know. If
Yeah.
you
Right.
do
So,
the
see the bottom line. Priyanka, what do you think? Can we do the average using the combiners?
7 plus 4, 11 minus 2, minus 2. My answer is no, because I'm not getting, if I do the individual, without combiner, if I calculate, I am getting different value. When I do with combiner, I'm getting different value. I'm not getting the same value.
Right. So that's what the thing is. We cannot guarantee that we'll get the same value if you choose combiner. So let's take the mean of this set, the same way the data set, right? So mean of this one is coming out as 30 plus 25 plus 15. If you divide it by, so how much is it coming? 40 plus 30, 70. And if you divide it by 5, it comes out as 14. Or it is 80. 40 plus 30, right? 70. Right? So,
Yes.
but if you take the mean of these three, it is coming out, and the mean of these three, so mean of 20, 10, 0 is coming out as 30 divided by 3, which is 10, and this is 40 divided by 2 is 20. So mean of 10 and 20, the final mean will become 15 instead of the expected 14. It will come out as 15 if you do the individual means and then try to do the mean overall. So what it means is, don't blindly use combiner. Use the combiner in the cases where you can really use and get the correct output. Okay. So combiner, while choosing the combiner, just ensure, like, if you're using a combiner with the same logic as a reducer, it should not impact your overall. It should not give you incorrect result because you have combined the data, right? So be careful while choosing the combiner. In the cases where you can use combiner, go ahead, use it. If in the cases you cannot, simply you cannot, right? So, and then there is a partition function. We discussed, like, partitioning of the data happens after the data is mapped, and this partitioning, what it do, uh, it just tells you, like, this key belongs to which particular partition, right? So all the similar keys will be partitioned with a value, and the default way to achieve the partition is a hash key, a hash algorithm. So it creates a hash value for each of the key and finds out, like, okay, this belongs to this partition, right? So once you have a data partition, then those goes to the reducer, and then it finally aggregates and give you the final output. Any questions, any doubts, anything so far in MapReduce?
No.
So did the download complete?
No, it may take 30 more minutes.
Okay, no problem. So if you just follow this, right, it's very simple. Let's say it tells you what has to be done. So Oracle VirtualBox is installed. Okay, host operating system, some of the things, some other prerequisites. Otherwise, it's very simple. So you just have to open this, and these are some of the screenshots you need to follow. You just have to run the VirtualBox. This is for the Mac OS. For Windows, you have this one. So file preference, right, and then you will, right, so file and then preference, and then import the appliance. So you just have to, on the Windows one, you have to click on file and then import the appliance. If you click on import the appliance, it will ask you for where is the location of that image file. Like this, it will ask you OVF. So you just have to browse this sandbox. So this is the downloaded file that you have. You just have to select this one, and it will come. It will show you this screen. Then you have to say next, and RAM. So whatever comes out as default. If you want to increase the RAM, you can give a little bit more RAM if you have available. RAMs, then so if you set 8 GB of the RAM to the Hortonworks sandbox, it will improve the performance. But in case your laptop itself is 8 GB, you cannot give 8 GB of the RAM to the Hortonworks, right? So all those things you can just adjust it over here, and then it will start the import process. So it will import it, and once it is imported, it will come as like this screen will come, and just have to click on the start, and it will start, and it will come over here, right? So try to do this steps, just go through step by step process, and you'll be able to get your VM up and running. Once this is up and running, from the next class we'll start some hands-on to run some of the HDFS commands. We'll try to do some of the MapReduce programs. Okay, so let's continue with the hands-on sessions from next classes. Okay.
Thank you.
All right.